Hello everyone. In this video, I'm going to just give you a quick recap from different formal proofs. The first one is deductive proof, the simplest and the first actually proof that you always see in discrete math, which is you have a sequence of statements that we know that all of them are true, and from each statement you actually just conclude the second one, and you go over all these steps until you actually prove from the hypothesis you reach to the conclusion. So basically in all of these different formal proofs that we have, you have a statement that you wanted to prove with that statement will usually written as if H then C, that H is called the hypothesis, C is called the conclusion, and basically it means that if H is true, we wanted to actually prove that we wanted to reach to this fact that C is true. So those statements that we prove are in this form. For example, let's actually just see an example that say if Y is greater than or equal to 4, then 2 power Y is going to be greater than or equal to Y power 2. So here the hypothesis is Y is greater than or equal to 4, and the conclusion is that 2 power Y is going to be greater than Y power 2 for all the values of Y which is greater than 4, greater than or equal to 4. The conclusion is true. Okay, here I'm going to actually show you one example that we prove it using a deductive proof. Here I have two theorems, theorem 1 and theorem 2. I'm assuming theorem 1 is true. I am not actually proving that one. I'm assuming this theorem is true. I wanted to use that to show that theorem 2 is true. So to prove that theorem 1 is true, you can actually find the theorem in your textbook. It is actually using a different proof. It use in fact inductive to prove it, that we will actually discuss later. But for now, just for the sake of simplicity here, just assume theorem 1 is true. I'm going to use it to prove theorem 2 is true using the deductive proof. Here is a thing. We know that the hypothesis of theorem 2 is telling me that X is the summation of a square of 4 positive integers, right? So this hypothesis can be written as X is equal to A power 2 plus B power 2 plus C power 2 plus D power 2. And also the other part of actually the hypothesis is that A is an integer number greater than or equal to 1. Actually it tells me that all of these numbers A, B, C, and D are positive integer numbers, right? Positive integers. So if it is a positive integer, it should be greater than or equal to 1, right? So this is a part of the hypothesis. This is also a part of the hypothesis. We know that they are true because we wanted to actually go from knowing that they are true. We wanted to prove that this statement is true. So if A is greater than or equal to 1, B is greater than or equal to 1, also C and D, one thing that I can conclude is that A power 2, the square of all these numbers are going to be greater than or equal to greater than or equal to 1 as well, right? So this is something that we can conclude because they are going to be just the square of something greater than 1. Then I can actually add up all of these numbers. By adding all of these numbers, you can actually reach to X and reach to this fact that X is going to be greater than 4. You can conclude this from 1 and 2, right? Which X is the summation of all A power 2, B power 2, C power 2, D power 2, and all of these are going to be greater than 1. So the summation of them is going to be greater than or equal to 4. okay? And using the theorem 1 that we know it is true, we can now conclude that 2 power x is greater than or equal to x power 2. Okay, so as you can see, this was just a couple of steps that always we know something is true, and from that you can just directly conclude something else. So this is just a couple of steps to, deductive proof is the most intuitive way to prove something. I'm sure you have used it in a real world, not only in discrete math, to prove any logical thing actually. So when we are actually just writing our theorem, this is just different ways of writing the same thing. You wanted to write a theorem that in the form of if the hypothesis H is true, then you can conclude C. You can write it as if H then C, or you can write it as H implies C. You can write it in this form. All of these are different actually mathematical form of representing the same thing. Or you can write it as C if H, which basically tells you that C is true if H is true, which is exactly the same thing as you say if H is true, then C is true. The other form is H only if C, which means that H is true only if C is true. Or whenever H holds, C follows. Doesn't really matter, these formats. I just wanted to actually remind you that you can actually rewrite theorem in different forms. All of them are equivalent. Again, just a recap about the quantifiers for all and for every. This is the symbol for all. For example, the previous theorem that we wrote, that for all positive numbers which are greater than or equal to 4, we can actually write it in this form. For all x greater than or equal to 4, this is the conclusion. So this is the hypothesis part of it. This is the quantifier that say for every, for all. And this is the very mathematical form to write that theorem. The other quantifier that we use a lot is there exist, which we use this actually symbol to show it. Okay, the next proof that I'm going to cover here is inductive proof. Basically, whenever you are working with some recursive definitions, objects, or whatever, if you're proving something about it, inductive is going to help you a lot. So especially if you are working on some more complicated structures. For example, you are going to prove something about trees. You are going to prove something about graphs, something in that you can actually rewrite the definition in a recursive format. Inductive is going to help you a lot in all of those proofs. We have two different actually forms of proof: simple induction or structural induction. Simple induction usually actually is used to prove something about the integer numbers. It is very simple. I'm going to show you some example. But structural inductions are more complicated. Basically, whenever you are working on some recursive concepts or some structures, graphs, or whatever, that you define some recursive definition for them, we will go with the structural inductions, like trees, expressions, so on. So basically, in any induction, you have two steps: basis, and the second step is inductive step. So let me actually just explain them over the simple induction, which is induction on integer numbers, and then we will see an example over about the structural induction. In the simple induction, you have a statement that you wanted to prove it. That is a statement that that's a theorem that you wanted to prove it. So usually that statement is written as in the form that S of n. Basically, n is going to play an important role in your statement because n is going, your theorem is talking about n. Okay, so an example is, for example, let me actually just show you an example here that you can see here. I wanted to prove a theorem like this, that for any number n greater than or equal to 0, the summation of all the numbers from 1 to n is going to be, the summation of all the square numbers of I equal to 1 to n is going to be this. So you can see that the whole statement, in fact, is about n, right? It actually goes around n. That's why we can actually write it as in a form of S of n. So we have a statement like S of n. The whole theorem will be written as S of n. You wanted to prove this S of n. There are two steps. The base step is that you show S of I is true, where I is the basis, is the smallest number that the statement is true for it. Usually it is 0 or 1, but in some cases, just depending on what is the theorem that you are proving, just find the smallest integer number that the statement is true for, that is going to be the basis. The inductive step is that we assume S of k for all the values k greater than or equal to that basis is true. Okay, this is the assumption. And then from this assumption, you should prove that S of k plus 1 is also true. So assuming S of k is true, you should prove that S of k plus 1 is true. So in any inductive proof, you have two steps to prove. You have to show basis and you have to show the inductive step. That basically is just proving this part, that assuming sk is true, you should prove S of k plus 1 is also true. So if you do both of these two steps, it actually show that for all the numbers n, the whole statement S of n is going to be true. And the reason basically is that you are showing that for a small number, some smallest, some basic, some base number, this is true. And then you are showing that, okay, from this base, you can, it's a kind of recursive thing that, okay, from that base thing, you can actually show that because you have already showed this, you can show that for, you already showed that for I it is true. Then you can, because this is true, you can say that for I plus 1, this is also true. So S of A is true. Then S of A plus 1 is true. Then S of A plus 2 is true. Then S of A plus 3 is true. So basically, it actually goes to infinity. Basically, S of n for any number n is going to be true. The whole theorem has been proved. So now you can see that how closely, the close relationship between induction and recursion. Inductive proof is very useful. Most of the time, if you can't go with anything else, probably you can go with inductive proof. So don't never forget about the induction. So now let's get back to this example that we wanted to prove that for any number n greater than 0, the summation of the square numbers between 1 and n is going to be this formula. Okay, we need to first find the basis. We should show that, okay, so the smallest number that the theorem actually is valid for, holds for, that is going to be 0. So when I is equal to 0, when n in fact is equal to 0, the whole formula is telling you that put 0 over the formula. So this is going to be 0 multiplied by 0 plus 1. I'm just actually following the formula here, okay? and 2 multiplied by 0 plus 1 divided by 6. The whole thing is going to be 0. And it is clear that the summation of all the numbers from 0 to 0, I mean all the square numbers from 0 to 0 is going to be 0. So we prove the base is true. The next part is we are going to prove the inductive step. We are assuming the theorem, the statement, holds for the value k. Okay, so we are assuming that this is true. This is our assumption. And from this, we wanted to prove that this formula is also true for k plus 1. So you can see that I have changed this one to go to k plus 1, and I have also put k plus 1 instead of n in all of these parts that I have n. So this is going to be the formula. I wanted to actually prove this. How can I do that? This is my assumption. It can be done simply like this, that okay, I wanted to see that what can I get from this. This is going to be the summation of all the numbers from for example 1, 2 power 2, 3 power 3 plus until k power 2 plus k plus 1 power 2, right? Excuse my handwriting. Okay, so this part is going to be exactly the summation of all the squares from 1 to k, right? This is exactly what I have here. So I can say that this can be written as, I'm just substituting that and write it as, okay, k to k plus 1. I'm just using this part, replacing this summation with this formula, that this is the assumption of my induction, 2k plus 1 divided by 6 plus k plus 1 power 2. Okay, and now what I'm going to do here is that just simplify this formula. Just to simplify that, that's going to be okay, k to, I'm just multiplying, I'm simplifying this one. Okay, k to k plus 1 plus 2k plus 1. This is going to be 2k power 3 plus 2k power 2 plus k power 2 plus k. Okay, this is just the expansion of this part, and I'm going to just get this one and put it over add it to the numerator. So plus 6, this is going to be k power 2 plus 2k plus 1, right? So it's going to be 6k power 2 plus 12k plus 6. So this is going to be the whole thing over 6. Just if you just simplify it a little bit more, just add up this one, this one, this one. This is going to be 2k plus 3, sorry, k power 3 plus 9k power 2 plus 13k plus 6. You see, I just simplified this statement, and this is going to be the simplest form of it, right? So now I would actually just stop here keep this one. The next part that I'm going to do is I'm going to simplify this formula. I have got some formula for this part. This is going to be here. So this is 1. I can write it as 1. Now I'm going to simplify the other side, 2. So let's actually just see that what 2 is going to give me. If I keep multiplying, actually simplify this one, multiply this one inside the others and continue. So this is going to be k plus 1, this is going to be k plus 2, this is going to be 2k plus 3, right? So if you keep multiplying all these things together, you would get k. First multiply to everything here. That's going to be k power 2k power 3, okay, plus I think it's gonna be actually just too long if I continue doing all these multiplication. I do have it here. I have simplified, if you do this multiplication, if you simplify this form, you would actually exactly reach to this one, which is exactly what I got from, in fact, this part. I'm skipping it here in the video because it's going to actually take a long time for me to just write everything down. And you can actually do it on the paper. But be careful, don't skip this proof. For all the examples that you do, just do it on your own on the paper. So when you're doing it yourself, then you would never need to memorize it because you will digest it better. Here is another example of the induction, the simple induction over the integers. This was the example that this was the theorem that we used to prove the theorem 2 when we saw the first deductive example. We can in fact prove it using using the induction. I'm going to I have written down all the proof. Let's just discuss it. It's not going to take too long. Okay, this is the theorem. We wanted to prove this one, so we need to first prove the basis. Anyway, it actually tells me that the value of x should be greater than or equal to 4. So the smallest value for x is going to be 4. So the basis is 4. It is clear that 2 power 4 and 4 power 2 is both 16. So the statement is correct. So we proved the basis. The inductive step is that we assume the statement is correct for k. So this is our assumption. We wanted to prove that it is also correct for k plus 1. Okay, let's actually start from 2 power k. If I multiply 2 to both sides, I would reach to this, right? We know that this is, we know that this is true. So if I multiply both sides to 2, still 2 multiplied by 2 power k is greater than 2 multiplied by k power 2. So this part is going to be 2 power k plus 1. So this is going to be the left side of the statement that we wanted to prove. And the other side is 2 multiplied by k power 2. Okay, what is the relationship between this one and this one? If I prove this is greater than or equal to k plus 1 power 2, I'm done, right? Let's just use a different color. If I can prove this, I'm done. I will actually just show that this is also true. So if you simplify it, if you open this one, this is going to be k power 2 plus 2k plus 1, right? So by comparing this side and this side, you will see that, okay, this side will be removed and the 2, so you remain with this. I need to prove that k power 2 is greater than 2k plus 1. Again, I can actually simplify this and reach to this one, that k is greater than or equal to 2 plus 1 over k. And this one is simple to prove. Why? Because we know that k is going to be some positive integers greater than or equal to 4, right? So 1 over k is going to be always less than or equal to 1 over 4, right? Because the value of k, when k actually goes to infinity, 1 over k basically goes to 0, approaches to 0, right? So the largest value for 1 over k is going to be 1 over 4 or 0.25. So basically you are just, this is obvious that k is greater than 2 plus k is greater than 2 plus 1 over k, because it means that k is going to be greater than 2.2.5, which is greater than that because k is greater than or equal to 4. So we are done with this proof. The next example is going to be an example over inductive proof. A structural induction. To be able to actually give you this statement, the statement that I wanted to prove is this theorem that assume you have a full binary tree and n t is going to be the number of leaf nodes in a full binary tree. We wanted to prove that in any full binary tree, this statement is true, which actually tells me that 2 multiplied by the number of leaf nodes is minus 2 is equal to the number of edges. So 2 multiplied by the number of leaf nodes minus 2 is equal to the number of edges. What is a full binary tree if you don't remember from COMP382 or from the discrete math? This is the definition of a full binary tree. A full binary tree is going to be a binary tree that all the nodes are either a leaf node, which means that it doesn't have any child, or it exactly has 2 children. Okay, so this is going to be a full binary tree, but so this is not a full binary tree. Not a full binary tree. Why? Because this is not a leaf node and this doesn't have actually 2 children. Or for example, this one is not a leaf node and it doesn't have 2 children. So this is not a full binary tree, but this is a full binary tree. All the nodes are either have 2 children, or they are leaf nodes, 0 children. Okay, and what does that formula told us? The statement that the theorem tells me that 2 multiplied by the number of leaf nodes minus 2 is equal to the number of edges. How many edges you have here? The number of edges here is going to be 1, 2, 3, 4, 5, 6, right? How many leaf nodes you have? 1, 2, 3, 4. So 2 multiplied by 4 minus 2 is going to be 6. Yes, it's exactly equal to the number of edges. Okay, that was the theorem. We wanted to prove this theorem. So what should we do? Here one thing is that if you wanted to prove this theorem not using induction, this is going to be very complicated. If you wanted to actually prove this theorem using induction by this definition, also this is going to be very complicated. one thing that I can do to simplify my proof is that I can, whenever you are going to use a structural induction, be careful, you should find a recursive definition for your structure. Here our structure is a binary tree, a full binary tree, right? And I wanted to prove a theorem about this structure. If you are going to use a structural induction, you'd better define a recursive definition for your structure, and then that recursive definition helps you a lot in actually simplifying your in your inductive proof, your structural induction. So I'm sure that I'm not sure that all of you have taken COMP381 with me or not, but if you had, you remember that I emphasize on the recursive definitions a lot. For almost for everything that we discussed, I give you some recursive definitions. The recursive definition for full binary tree here is I've written actually a recursive definition for the full binary tree. In any recursive definition, you have two parts, just like induction. You have a base case and you have some recursive part. The base case is just actually tell that what is the simplest form of a full binary tree. Any tree with just one node is going to be a valid full binary tree. And if you actually just compare it with the definition of full binary tree, is that the definition of full binary tree is that all the nodes are going to be either a leaf node or a node with exactly two children. A single node is going to be a leaf node, so this is a valid full binary tree. The recursive part of a definition here is that we would say that a tree is going to be a valid full binary tree if the root has two children, exactly two children, and both of them are going to be a full binary tree. This is a recursive part of it, that the subtrees here, T1 and T2, this subtree is a full binary tree. This is also full binary tree, right? And R has exactly two children. So the result is going to be a valid full binary tree. Okay, so now I'm going to use this recursive definition to prove this theorem. How can I do that? Remember in the inductive and in any induction, you have two cases, right? The base case that you should prove the theorem for the base. So the base of your definition or your full binary tree is that the simplest full binary tree is going to be a tree with exactly one node, right? I'm going to show you that, yes, this is going to be the basis of our structural induction. So if your tree is only one node, so the number of leaf nodes n of t is going to be 1, right? How many edges you have? The number of edges is going to be 0. If you only have one node, the number of edges is 0. The number of leaf nodes is 1. And the theorem holds, right? 2 multiplied by 1 minus 2 is equal to 0. So we prove that the basis is correct for our induction. The inductive step tells me that I should prove that this statement is correct for, I'm assuming that this statement is correct for all inductive step. So our hypothesis is that is that this theorem is, holds for any full binary tree with leaf nodes equal to k, or anything smaller than that. Okay, remember that s of k, we assume that is correct. We wanted to actually just prove that for any binary tree with leaf nodes equal to k or less than k, the theorem holds. So let me actually just write it as less than or equal to k. For all the binary trees with the number of leaf nodes less than or equal to k, the theorem holds. We wanted to prove that it is also correct for proof it is true for the trees with the leaf nodes equal to k plus 1. Okay, so any binary tree with the leaf nodes equal to k plus 1, based on this definition, is going to come from this the recursive part, right? So basically your tree is going to have a root node that has exactly 2 children, and this is going to be a full binary tree. This is going to be another full binary tree. So it has there are some leaf nodes here and there are some leaf nodes here. Okay, so let's just call this one T1, let's just call this one T2, right? So the number of leaf nodes in this tree that we wanted to actually prove the theorem for, that is going to be the number of leaf nodes in T1 plus the number of leaf nodes in T2, right? There is no other leaf nodes. But basically this tree is going to be just created by the number, all the nodes here and all the nodes here, and you just added a root node to that, and the root node is not going to be a leaf node, right? So every leaf node that you have is going to be either here or here. So the number of leaf nodes in T is going to be this equal to the number of leaf nodes in T1 and equal to plus the number of leaf nodes in T2. So definitely the number of leaf nodes in T1 and T2 both of them are going to be greater than or equal to 1. If not, if the number of leaf nodes is 0, it means that the whole tree is empty and you don't have any, so it's not going to be valid. So in that case, what I can actually conclude here is that because the summation of these two is going to be equal to k plus 1, I can conclude that the number of leaf nodes in T1 is less than or equal to k, and the number of leaf nodes in T2 is also less than or equal to k. Okay, so because I know the number of leaf nodes in T1 and T2 are less than or equal to k, I know that the theorem will hold for them. Okay, let's just use a different color here. So the theorem holds because of the the inductive hypothesis. So I know the 2 multiplied by the number of leaf nodes here minus 2 is going to be equal to the number of edges in T1. And the theorem holds for the other part, the number of leaf nodes in T2 minus 2 is equal to the number of edges in T2. Okay, so one thing else that we know is that the number of edges in T is going to be the number of edges here, plus this one, plus this one. So the number of edges in the whole tree is going to be the number of edges in T1 plus the number of edges in T2 plus 2. These are the two edges that has been added to add the root to these two subtrees. Okay, so what I'm going to do is that I'm going to just add these two. I'm going to basically just follow this and see that what I can get. So the number of edges is going to be the number of edges in E1 plus the number of edges in T2 plus 2. For this one, I'm going to use this formula. For this one, I'm going to use this formula, and let's see that what would I get. So 2 multiplied by the number of leaf nodes in T1 minus 2 plus the number of 2 multiplied by the number of leaf nodes in T2 minus 2, and at the end plus 2. So this part, this part, this part, this part. If you just add all of these up, you would get 2 multiplied by the number of leaf nodes in T1 plus the number of leaf nodes in T2. This minus 2 will be removed by this minus 2. And you can see that this is going to be the number of leaf nodes in T, right? So this is going to be 2 multiplied by number of leaf nodes in T minus 2. This is exactly the formula that we wanted to prove. So we are done with our proof. In the slides, you can actually find out all the full proof here. So don't worry if you couldn't actually read my handwriting. I have the full proof here written for you. Okay, I'm going to basically wrap up this lecture. There are a couple of other ways to prove, which are very actually famous. Proof by contradiction. So basically in proof by contradiction, again, the statement that we wanted to prove is that if H, then SC. Okay, so the way that we prove it in proof by contradiction is that we assume C is not, we assume H is true, but C is not true. And from this, we should actually just reach to contradiction. So what we are going to do is that if H holds, but C is not true, basically the negation of C is true, it would actually conclude to contradiction or implies falsehood. An example, for example, you can actually just prove that, assume that for all, I'm going to actually give you an example. The statement that we want to prove is that for all integer numbers n, if n power 3 plus 5 is odd, then n is even. I can actually do this using, prove this by contradiction. So basically what I would do is that I would assume n power 3 plus 5 is odd. Is odd when actually I'm saying that, let's just write it in this way. This is odd, so basically you can actually write it as 2 multiplied by k plus 1, some k, I don't care what is it. And I would also assume n is even is your c, so negate c would be, which is this one, negate c would be, n should be odd, so you can write it as 2j plus 1. Okay, so from these two you can actually conclude that when n is odd, so n power 3 will be, if I simplify that, 2 power j plus 1 power 3. If you actually simplify this, it's going to be, I guess 8 multiplied by j power 3 plus 12 multiplied by j power 2 plus 6 multiplied by j plus 1 power 3, as far as I remember. Yeah, I think so. So this is going to be n power 3, then n power 3 plus 1 is going to be whatever we have here, so 8 j power 3 plus 12 j power 2 plus 6j plus 1 plus 1. Okay, no, be careful here. You can see that this is going to be, let's just actually just write this 1 plus 1 as 2. So I can factor out 2 here. So 2 multiplied by 4 j power 3, 6j power 2 plus 3j plus 1. This is going to be, why I did it plus 5, plus 1. I should actually write it as plus 5. So here it would be plus 6, and it would be, okay, I wanted to actually reach to this fact that if n is odd, n power 5 cannot be odd. You can actually just get from, this is a proof by contradiction, because here you got 2 contradiction, because this is not odd, it is even. Okay, so basically in any proof by contradiction, you assume that the hypothesis is correct, but the conclusion is false, and you reach to contradiction at the end. Here I just have a question for you. Assume that you wanted to prove some statement like this, that the statement tells if A and B is true, then C is true or D is true. If you are going to prove this by contradiction, what should we do? The thing is, here you should be careful. If you are making the conclusion, you are negating the conclusion, be careful. Don't take this statement, this theorem in this form that the whole thing you should actually negate it. If you do that, your proof by contradiction would be something like this, that proof that A and B, this is the hypothesis, is your hypothesis, and also the negate of C or D. Okay, this is this is wrong. What you should prove is basically is this fact that this theorem, in fact, is two theorems. This theorem is, this theorem has two parts. You can basically should write it as A and B implies C or D. Okay, you should basically write it in this way, and when you are actually proving by contradiction, what you should prove is that A and what you need to prove is has two parts, A and B, and not C reaches to false, and also A and B and not D also reaches to false, reaches to contradiction. So if you have a statement like this to prove, you have to prove two things. A and B and not C is false, and also A and B and not D is false, or reaches to contradiction. And the last actually technique is proof by contrapositive. In proof by contrapositive, instead of actually proving if H then C, you would rewrite it as if not H then not C. Okay, so you prove this statement instead of this statement. This statement is a contrapositive. This statement is a contrapositive of the other one. So it doesn't matter if you prove this one or this one. Both of them actually implies each other. But be careful. This is different than proof by contradiction. In proof by contradiction, you would start it with H and not C and reach to contradiction. Here you just actually write the contrapositive of your statement, and maybe because, in some cases, maybe the contrapositive is easier to prove, so you go with this way. And the other actually proof is by counter-example, that someone claims something and you wanted to say that no, this statement is not true, it is false, so you find a counter-example, and you will show that no, your statement, your claim is not true, is not correct. But be careful, we don't have any proof by example. So if you wanted to prove a statement, it's not enough to just write down some example. Even if you write millions of examples, it's not going to be a valid proof for a theorem, because there is still a chance that maybe that theorem is wrong for some example that you haven't covered. So basically, because you cannot cover all the examples, all the possible examples, when you are proving something, you should use one of these formal proofs that we discussed. You cannot just write some sample examples. Okay, I'm gonna actually just finish this lecture. The last thing that probably is good to write is that if and only if. So far, all the statements, all the theorems that we have seen, all those examples were in the form of ifs, H then C. So from the hypothesis, you reach to the conclusion. But some theorems is in the form of if and only if, which basically means that from A you can reach to B, and from B you can reach to A. So this form of theorems has two parts. The if and only if sometimes will be abbreviated as IFF. If you are doing a proof, you are proving a theorem which has if and only if a statement, your proof is going to have two parts. You should start from A and show that if A is true, B is true, and you should also show that if B is true, A is true. So it will double your work. You have to do two proofs. From A you should reach to B, and from B you should reach to A. There are plenty of examples in your textbook that you can check. So I'm going to finish this lecture here. That's going to cover chapter 1.